Last month's demonstration was on hacking a ShopBot Handibot. That's how we created the Frankenbot. The demonstration video was provided with the July CNC user group minutes. We also provided a toy mirror SVG file, which you were to use for the August exercise. In my case, I used the Aspire 9.5 release, which I purchased on the internet. And then I saved the toolpath to my laptop, and that approach is discussed in this presentation. Alternate applications that you could have used were the free Makerspace version of Grbl Pro or OpenBuild's CAM software, or any CAM software that you prefer to use. CNC workflow can be broken down into three major steps: design, toolpathing, and machining. CAD software is used to design your project. In this case, I used Inkscape. Toolpathing is typically done with CAM software, and in this case, I used Aspire 9.5. Machining is done using control software, and in this case, I used OpenBuild's control software. Next, I will show you how I use the Aspire software to generate the toolpathing. Aspire 9.5 was covered by Bud Bensick in a previous video, so I will not go through all the tools, just the tools I use for toolpathing. To generate the toolpath using Aspire, the first thing I did was open the application. And this is the home page, and the first button I click is Open an Existing File. Shown here are the two files that we sent to you for the August exercise, and I selected the PDF. Job setup is where we define how we want to work on the material blank. In this case, the job type is single-sided. The job size will be 4.5 inches wide, 7.5 inches high, and about 1/3 of an inch thick. The Z0 position is going to be on the material surface, and the XY0 position is going to be in the lower left-hand corner. Notice I worked this task from top to bottom. After I've completed those steps, I simply click on OK. The drawing dialog can be used to modify the files that you imported. In this case, I did not need any of the items that are on the left-hand side of the screen. I only needed to select both of the SVG vectors and center them on the board. Selecting Toolpath on the upper right-hand side of the screen brings up the Toolpath dialog box shown here. To design the first toolpath, first select the mirror pocket vector in the center of the screen, then select Pocket Toolpath Operation to open the Pocket Tool dialog box. Design the Pocket Toolpath by working from top to bottom. The steps I used were cutting depth, tool selection, clear pocket, tool ramp plunge move, safe Z. I named the tool path, and then I clicked on calculate. The pocket cut starts at the top of the material, or Z0, and continues on down to the bottom of the pocket, or Z equals minus 0.08. Tool selection sets up the cut depth and the step over that the tool will move as it cuts through the pocket. It also sets the feed rate and the plunge rate. It does not set the spindle speed. The spindle speed is a recommendation of 12,000 RPM, and I will have to set that on the router before I begin the cutting operation. I'm only using one tool in this operation, so I can skip the next step. We clear the pocket using an offset path in the climb direction, so that's what I've selected, and there's no pocket allowance required. Tool ramp is the motion we give the tool as it plunges into the material. In this case, we've selected a 1-inch ramp. Safe Z is the distance the tool is moved in the plus Z direction before moving from the home position to avoid accidentally cutting into the wood blank or impacting clamps during router repositioning from the 0 location. In this case, we've selected 0.2 inches. Next, we name the toolpath. A toolpath name convention can provide good information for the future. In this case, I've used project, toolpath, type, and tool, TM pocket 0.25 EM. Clicking on calculate then opens up the preview toolpath dialog box. I'm not going to run a simulation at this time, so I'm clicking close to return to the toolpath menu. Next, I'm ready to design the second toolpath. In this case, it's the outside profile of the toy mirror. I click on 2D to view and see the second vector path. Then I select the toy mirror profile vector and then select the profile toolpath. This then brings up that dialog box. The profile toolpath is pretty much designed the same way we did the pocket toolpath, except it's a separate dialog box. In this case, we do the cutting depth, the tool selection, the machine vector. We add some tabs in this case, which we didn't do in the case of the pocket. We'll do ramping, we'll have a safe Z, and again, we'll name the toolpath and then do a calculation. Adding tabs to the toolpath is very important in this case because when we cut the profile, we will cut through the material. I know I've got it stuck down with double-stick tape, but as a second level of insurance, it's nice to have tabs in position to hold the mirror blank in place as it's cut from the material. So I click on Add Tabs. It brings up this dialog box, and you can see the tabs are 0.2 in length and 0.2 in thickness. Then I click on Locations to add the tabs. And I pick locations where once I pull the mirror out of the blank, I can easily sand those locations. So it's very important to select the proper locations for the tabs. Clicking close opens the 2D profile toolpath menu. A common warning that you will see using this application is cut through. We plan to cut through the material, so the application is just warning that the tool depth will go beyond the bottom of the material. Pressing OK will continue with the toolpath calculation. After the toolpaths are saved, a preview toolpath screen is opened. The image can be rotated and examined by clicking and dragging it with a mouse. Then to see the toolpath simulation, select Reset Preview and then select Preview All Toolpaths. Here's an example of how you can rotate the blank to see where the paths will be cut. And then when you're done looking at that, you can reset the preview and run a toolpath simulation. The toolpath cuts a pocket, then it cuts a profile, and by rotating the blank, I can see where the tabs will be cut. It's not absolutely necessary, but after I run the simulation, I typically click on the Calculate button to recalculate all the toolpaths. Once I see that the toolpaths are all successfully recalculated, I click on OK, and then I close this dialog box to open the Toolpaths dialog box. Click on the icon shown to bring up the Save Toolpaths dialog box. Now we want to save the toolpaths as one file. Note that the two toolpaths are now combined as one file. And I can do that because I'm using one tool. If I click on the down arrow next to post processor, it opens up a list of post processors that we could use. We want to select Grbl mm G-code file and then click on the Save Toolpaths button. Finally, I retitled the joint toolpaths as Toy Mirror 08/21/21, the date that I created this file, and then save the file to my laptop, or if I'm bringing it to Xerocraft to print there or cut there, then I put it on a memory stick. Now that we have got our file for the toy mirror project, it's time to select the Spoilboard setup. The existing Spoilboard on the Xerocraft large format CNC is large enough to hold the Handibot. However, in this case, I decided to use a dedicated toy mirror project Spoilboard. As you can see in the picture, it has two long boards that the Handibot rests on, and there are four corner stops, and the toy mirror project is double stick taped in the middle of the two boards. That's what I use for small projects. It's also designed to hold long boards, and I'll show you long board hold downs using clamps in the next slide. Gravity will hold the Frankenbot on the Spoilboard. The weight of the machine is sufficient to hold it down. The four corner stops keep it from moving laterally. The pass-through Spoilboard setup is shown in the picture on the right. The pass-through setup enables quicker duplicate routing operations. Here, a 5-inch wide board is being cut in a 9-inch pass-through slot. The board itself is around 5 feet long. Passing long boards under the Frankenbot allows multiple cuts from one board in one control software setup. I use two 1/4-inch T-rails spaced 9 inches apart, which is the Frankenbot width capacity. A temporary spacer positions a 5-inch wide project board to the X0 position. Then 4 clamps secure the project board during the router cutting operation. Now we simply mount the Frankenbot, apply our connections, turn on the power, and open the control software. We mount the Frankenbot by aligning the base to the corner stops. We apply the power cord, the dust vacuum hose, and the USB computer interface cable. Then we turn on the Frankenbot power and set the speed to 3, which is about 12,000 RPMs. That's the recommended speed for the 1/4-inch end mill. Then we open the control software, which is Open Builds Control version 1.0.304. Now we can use the Open Builds Control software to simulate the run and set X, Y, Z 0. The first thing we want to do is open the G-code file right here. Next, we'll run the simulation. Running the simulation will demonstrate how the cut will be made on the project board. Third, we connect the software to the Frankenbot using the Connect button. And then we home the router. When we home the router, we've set up the Toy Mirror Project XY datum. Therefore, the next step is to 0 X and Y using these two controls here. Finally, we'll use the jog controls to set the Z0 position. And I'll explain that in the next slide. You can set Z0 using jog controls on a piece of paper. You want a precision motion on the bit, so the first thing you do is you select incremental jog. In this case, I also set the desired jog increment to 0.1 inch. Move a piece of paper under the bit and lower the bit to the paper using the Z- button. When you feel a slight drag on the moving paper, Stop moving the bit and set Z0. In the future, we will upgrade this process by using the Frankenbot Z0 sensor. To run the toy mirror project, select Run Job. Then observe how the tool is moving. Make sure that the toolpath is what you expect, and make sure the project material is not moving. In the interest of full disclosure, I did forget the spacer for the first pass-through cut. Consequently, the profile cut ran off the board. After adding the spacer, I successfully ran a second cut without having to rezero. In summary, it looks like it takes a lot of steps to set up the Frankenbot, but it really only takes about 8 minutes or less. Aspire 9.5 is not a long learning curve. You just need to work top to bottom from the left side to the right side. Very few steps are required to repeat design cuts. Frankenbot is best suited for small projects like the toy mirror. The machine is portable but heavy, so you could probably skip the gym that day. It's great for multiple cups using the feed-through Spoilboard. We recommend consider using the Frankenbot for small multiple copy projects. Design and use a dedicated project Spoilboard setup so that you can easily repeat your cuts. For any further information, please contact Adrian Barton or Terry Glover. Thank you for your time. For more information on the terms, tools, and software used during this demonstration, please see the attached references.